Okay, no problem. Go ahead.
So Rolando, good morning. So I'll switch to English, I think. I will shortly introduce myself, and I'll talk a little bit about statistics, econometrics, and other related things, so that you can get used to my English and to my pronunciation, and then we'll start with statistics, econometrics. So my name is Econometrics. I actually from Viva. I studied pure mathematics at the Ivan Franko University here. After mathematics, I went to Germany to do my PhD and to do my postdoc in Frankfurt. After that, I was assistant professor of econometrics at the University of Bern in Switzerland, and then during the last, since 2011, I think, I'm professor of statistics at the University of Augsburg in Germany. Augsburg is like 60 kilometers to their west from Munich, so we have a close cooperation with our Munich University there. What I do at their chair of statistics, so I'm head of the chair of statistics there. The offer of the chairs in Germany and generally in Europe, they are slightly different from their chairs in Ukraine. So the chair usually has just one professor, like maybe 5 to 10 assistants or lecturers. And we offer all the possible courses which are in some sense related to statistics, econometrics, data mining, and so on and so forth. So what we teach, particularly I teach a course of statistics 1 and statistics 2. Maybe one important thing, I am at the faculty of business and economics, so all our students have major either in business or in economics or in some business IT or mathematical economics, so very different things, but they are in some way related to business and economics. So what are the classical syllabus of our students is that they get one course of statistics 1 and statistics 2 at the very beginning. It's like mandatory course, everyone has to do that. Then they get a course in mathematics 1, mathematics 2. It's also a mandatory course. And then they have plenty of different choice courses, like I give, for example, a course of mathematics for finance, or data mining course, risk management course, and all other possible things. And at the master level, we have a mandatory course of econometrics. It's really a hardcore econometrics course. And they have also plenty of optimization, which is optimization courses, which are given by our chair of mathematical methods for economics. So the course which is here, it's like a combination of the things which I also teach at our university. It is heavily compressed because actually these things are taught in Augsburg during 3.5 semesters. And here it's going to be like very compact form of that. Another problem, because I do it already here for the 3rd time or for the 4th time, is the very heterogeneous background of the students. So some of you, at least in the recent years, some of the students started pure mathematics, so most of the things were pretty simple. But there were also plenty of students who had a very background in social sciences. Then it was difficult on some slides just to follow what we are talking about. So you also see on this slide that there are many simple slides where we go really deeply through all the things, but there are several really very mathematical slides. So just I wanted to show you with those slides that the things that we are discussing, they do not remain at that level, and there is an infinite level of complexity we can, in some sense, exaggerate or make it more complex. So that's about me and roughly about the course. We'll go to the structure of the course in a couple of slides. But now, why do we need this kind of course if we work with data science, with machine learning, with data mining, and so on and so forth? Actually, let's say, let's start from the very beginning. So in Europe, there is a problem with statistical literacy. So the normal people, they have problems in interpreting some basic statistics and basic numbers. Maybe if you've seen, there is a very nice book, Factfulness. I've seen yesterday a translation to Ukrainian. It's called Faktologia. The book shows actually on a very simple examples how heavily people misinterpret very simple statistics and simple numbers. So if someone says that the average salary is that and that, then many people just stick to that number and believe in that number. So those who really like such misunderstandings in statistics, I would really recommend this book on factfulness. So the problem is that people have problems with their basic statistics. And this means that if you go to very complicated stuff, like some very complex machine learning tools, everything what you have to bring to get some better feeling of those machine learning tools becomes really complicated. So the whole machine learning is like a mixture of IT, it's a mixture of optimization, it's a mixture of statistics and econometrics together, and like pure mathematics in some sense. This implies that machine learning on its own is a very complex field because you have to bring all those things together. I had, like maybe last week or two weeks ago, a talk with the head of data science or data analytics department of one of the largest German retailers. They have shops all over Germany, and the problem is that they missed this data science hype, so to say, in the recent years, and now they really start investing in that. They hired already 50 data scientists in the previous years, in the previous months, and they plan to hire another 50 by the end of the year. So my question is what your data scientists are doing. Because the problem is that many of my students, even they started the data scientists afterwards, but they end up with some Excel sheets. Doesn't really make them happy. And I was asking this guy what your data scientists are doing. And in fact, those guys, they are really going deep into their methodological part, into the data science part. They are not really coding anything because they outsource all their IT questions, all the implementation to some small companies, some startups. What the guys are doing, they are really trying to connect the business problem they have with some methodological tools which might be useful for them. So the problem is that every data scientist, he has to have some background in statistics, has some background in optimization, general mathematics, business, and so on and so forth. Now, why statistics? Just imagine that you missed your math course or math classes at school. Like the first 8 years, you go to their 10th grade or to the 11th grade, and the teacher asks you to compute some or like, to optimize some function to find minimum or maximum. Everyone knows that you have to take derivatives, set it equal to 0, solve this equation, and just say, well, the minimum is at this point, the maximum is at that point, because the second derivative is positive, negative, and so on and so forth. Now imagine that you missed the first couple of years of school. So you don't know how to add numbers, you don't know what are real numbers, you don't know what is a function, you don't know what is that tangency to a curve of a function, and so on and so forth. So simply not able to solve this problem. It's not possible to explain this problem of taking derivatives and maximizing the function to someone who has no knowledge of those previous fields. The same with machine learning and data science. So it is difficult to explain to someone what recurrent neural network. If someone has no feeling what is a time series, how can we characterize a time series? What are simple models for a time series? It is difficult to explain to someone that multi-layer perceptron is a kind of non-linear model for data if someone has no idea what is a linear model for data. It is difficult to explain to someone what is vector propagation if someone has no idea what is a simple optimization. So the problem is that one has to start with some basic concept and build up on that. Another problem is that machine learning or data science became very simple nowadays. So there are some tiny packages which can, like you need like a couple of lines of code beyond the data preparation to fit a very complicated model to the data. I had ITs from time to time for like external, for companies like it's not managerial data science, but something in that field. And I was talking about random forests. So I spent like really 1 hour explaining what a random forest is. And then the guy is coming to me and saying, well, thank you very much for the lecture. We have been using data for random forest for half a year at the company, but we had no idea what it is. Why? Because there is a nice function random forest, and they just pull it with the parameters and they get some results and they are happy with it. But they just they say we are data scientists, we are using this stuff, but at the end, if you ask what you are really doing, that's really difficult.
Yeah. But if it's working for them, so what's wrong with it? Or they are losing money. Could you detect if they are actually losing money because they are making errors with this approach?
They will surely earn money, because if they haven't been using anything so far, if they start just with simple random forest, it's going to be fine. But there is much more what you can add upon that if you just can tune the parameters. If you look at the list of their calibration parameters, like the options for the random forest is huge. Of course, we can just take everything by default and our Python or whatever, they will do already something with that. But you can just put much more on top of that if you know how to calibrate this things. What is also that's actually a good question, because many people try to use extremely powerful things, just very small data sets. Not everyone has a big data set. For example, we had recently a small project with a company who, I know how it is in English, I also don't know how it is in Ukrainian, it's only in German. So they sell meat in some sense, and they wanted to have some forecasts for the sales for the next 3 months or so. And they came to us and said, well, we would like, also catchy words, we need some machine learning tools to forecast our sales. Okay, let's see what you have, let's have a look what you have. And they had just 2 years of weekly data. So they had like 100 observations in time, they had like 10 variables, and come on guys, you don't really need some complicated stuff. With this kind of sample, it's pretty sufficient to use some basic methods. Let's start with the linear regression just to look how it looks like. What are the forecasts? If this works fine, if your R-squared is like 80% and the out-of-sample forecasting error is small, you don't need random forest to model your 500 observations, because you will for sure have some overfit. Like you will calibrate perfectly your data to the model. Now, what is also kind of maybe the last point, because we spent all the time on those things, many people now put very basic things in the framework of machine learning. It's really killing me if someone says that linear regression is a machine learning tool. Linear regression is 200 years old. I think the first implementation of linear regression was in 1805 or 1807. So Gauss used linear regression to model their movement of the planets. And now if you say 200 years later that linear regression is a machine learning tool, it's very new, it's a kind of come on. Or logistic regression for classification. You go everywhere and you see, well, logistic regression is a cool thing for classification, it's very modern classification tool in machine learning. It's almost 100 years old. The first time logistic function was applied, not model, but logistic function itself, was also like 200 years ago. The full mathematical treatment of logistic regression was done in 1930 or 1925. So it's almost 100 years old. But we simply take some older things and put it into the current framework. Well, everything what is about regularization is also like 50 or 60 years ago. So the whole mathematical theory for regularization was developed, smoothing and so on was developed also like in the 60s or in the 70s. But now we put it simply in a more or larger scale in some sense. So that's like general background and a small motivation why it is important to start with the basic statistics to get a better feeling for more complicated problems and for more complicated tools. You've got the first part of the slide, so I'll go pretty quickly through them. And then we'll slow down and discuss in more detail the things which I believe are important or where we need some deeper knowledge or deeper understanding of those things. You have the slides, I believe. I write on the slides over here, and I can also upload later on the slides with my comments, so you don't really need to write together. So let's move on. So I will just go through the more relevant stuff because you have them anyway. I'll concentrate like on the structure on some things which I know. So the whole statistics doesn't matter what kind of course you take or doesn't matter what kind of book you take. is split into three main chapters or three main building blocks. The very basic one is the descriptive statistics. It helps you to characterize some data sets. So imagine you have a data, and you want to characterize this data, a huge Excel sheet with a couple of numbers or a couple of pictures. So the question is, how can we aggregate a data set, small one, big one, whatever, with a couple of numbers and a couple of pictures, so those numbers are interpretable. They help you to understand the data and help you to make some inferences from the data. Now, the second part, it is a probability theory. This part develops actually everything what is related to probabilities, to random variables, to characterization of random variables. Because the whole statistics is based in some sense on random variables and probability. Probability, it's a kind of simple. If you toss a coin, then the probability of getting a head is 0.5. The probability of getting tail is also 0.5. But of course, their concept of probability is much more complex. Now, the random variables, they play a key role in the whole statistic and the whole econometrics. Why? Because everything what you want to do with data, and you want to minimize some errors. You want to minimize the forecast error. You want to minimize the deviation between your point and some regression, or like nonlinear regression or whatever. So you try to work with some things which are unobservable, or the things which you cannot quantify in some sense. So everything what is unobservable in advance is a kind of random. So the random variables, they play really the key role in the whole statistic and the whole econometrics. Now, the third building block is the inferential statistics. The idea of that part is to take a data set, analyze this data set, and to make some inferences about the whole population. For example, you make there are some elections for presidency or for the government or whatever. You make a questionnaire, you ask 100 people about their preferences. This one will vote for that one, this one will vote for that one. And from this questionnaire, you want to make an inference for the whole population of voters. So you take a smaller subsample and make an inference about the whole. So that's why it is called inferential statistics. Methodologically, we have in this field everything what is related to statistical tests, to some confidence intervals, probability of the test, and so on and so forth. So we'll have just a couple of tests. There are zillions of different tests. We'll just try to keep that part more or less short. And finally, of course, since there is also such a field as mathematical statistics, there is infinite level of mathematical complexity of those things. So we can talk about point estimation of the parameters, which is typically called calibration in machine learning. We'll talk about non-parametric statistics. Everything what is regularization, like smoothing and so on and so forth, it falls into the non-parametric statistics field. Large sample theory, big data, also like a buzzword nowadays. From statistical perspective, it is like large sample theory. What happens if our data size, sample size increases? And finally, the Bayesian statistics. It is Bayesian statistics. It is the statistical concept of learning. So Bayesian statistics arises, for example, in Bayesian machine learning. There is a field now of machine learning which is based on Bayesian ideas, and we'll see today already a couple of very simple examples why this Bayesian statistics really well. So we'll go very shortly in some of those points here, but concentrate mainly on the other. So that's some blah blah blah. What you hopefully have seen. First thing, one question which you immediately have to answer in machine learning or in data science is, what kind of problem do you have? Do you have some problem of modeling or forecasting, or do you have a classification problem? So if you have, so we talk only about supervised learning. If you have a classification problem, it means that you have some classes and you want to assign every object to one class or to another class. Say if you have clients, you have good clients, you have bad clients. So you have some new guy or new lady, and you want to assign this person to one of two classes. Now, what does it mean from a mathematical point of view? From a mathematical point of view, it means that your outcome variable takes just two values, 0 and 1. from statistical point of view, it tells us that the objective variable, like output variable, has nominal scale. What does it mean? It means that we can distinguish between two objects or two elements, but we cannot say more than that. For example, marital status takes different values. You can be either married, you can be divorced, you can be single, whatever you want. You can distinguish between those states, but you cannot compute the difference. In mathematical sense, you cannot take this marriage minus divorce is something. You cannot say, or in most of the cases, you cannot say what is better, what is worse. So people who have some experience with marriage might be able to introduce some ordering into the things, but in normal way, you cannot say what is better, what is worse. The same with gender. So you can distinguish between a man and a woman, but you can not compute the difference, and you cannot say what is better, what is worse. So, for example, everything what is related to classification falls into the category of nominal scale for their output variable. So you can classify in 2 classes, you can classify in 5 classes, you can classify as many classes as you want, but your target variable has nominal scale. Then you have ordinal scale. Ordinal scale, you can distinguish between the two objects, but you can also say what is better, what is less, but you cannot compute the difference. So the difference between the two elements is not interpretable from economic point. Let's say rankings of, on Amazon.com, you have rankings of all the products with those stars. Well, you know that 5 stars is better than 3 stars, but if you take the difference between 5 and 3, it is of course 2, but this 2 has no mathematical or economic meaning. Why? Because this is kind of difficult. Imagine you have a product which has just 1 star, you have a product which has 3 stars, and you have a product which has 5 stars. So you have 2 stars difference between the best product and the average product, and you have 2 stars difference between the average product and the worst product. But those are different 2 stars. So the 5 stars product might be much better than the average product. Then the average product is better than their worst product. So mathematically, you have 2 stars in between, but economically, the difference might be completely different. So this difference is in fact not really interpreted. But you can say what is better, what is worse, and you can also say that the 5 stars product is something different than the 1 star product. So there are some tools and methods on that one. So they are especially like ordinal regression or special tools where you take into account that there is some order in the observations. And finally, there are several different scales for variables which can take any values, like temperature values. You can distinguish between -20 and +20. You can say that +20 is warmer than -20. And you can also say that the difference between +20 and -20 or 40 degrees is that a lot. So you can really interpret the differences between the degree of values. So mathematicians, they also give deeper. They assume that there is some 0 in there. In the scale, for example, you have price. 0 is a natural value for the price, like starting value for the price, or age is also a natural starting value for that variable, which is not the case for temperature, for example. So 0 temperature in Celsius is a very artificial value. It's simply the freezing point of water. You can also set it to something different, like in Fahrenheit rates. And finally, there is something like absolute value, but doesn't really matter. So we have to distinguish, in fact, between nominal scale, distinct values like colors, gender, marital status, ordinal scale, where the data is ordered, and all other scales where you can compute the difference and interpret this difference. Yeah.
Okay. What kind of data will be on the ordinal scale but not on the interval?
Rankings, like with the stars. So you cannot interpret the difference between the values. Or the grades, for example. What kind of grade scale is now? 12 is the best, or? In general, it's like 1 is the best one, 1.3 is the second best one, 1.7 is so on, so forth. So this difference, of course, I can mathematically compute the difference between 1 and 1.7, but this 0.7 makes no sense.
Also, maybe as example, hotel stars.
Yeah, it's like Amazon ranking hotel stars or restaurant stars. You know what is better, but the difference is very artificial. So that's about scaling. Qualitative, that's simple, but it's what you can get also from the slides. Frequencies. In many cases, we work not with the original data, but with some kind of frequencies. It's really very basic thing. So assume that we have our data, which is denoted from x1 to xn. xi can be any real number, can be on any scale in fact, and a1 to ak are all possible outcomes. So those are the realizations, the values which are really observed, and those are the possible outcomes. So imagine we work again about the rankings of the hotels. You take 100 hotels and pick up all the rankings. So the first hotel has 1 star, the second hotel has 5 stars, and so on and so forth. And then a1 to ak, a1 is 1 star, ak is 5 star. So those are the possible rankings of the hotel we have. So what we do, we can compute the absolute frequency of AI, denoted typically by n, and this is simply the number of their occurrences of the realization AI in the sample. In other words, n of 1 star is going to be the number of hotels, of 1-star hotels in our sample. We can also compute the relative frequency, which is the number of hotels with 1 star divided on the number of the hotels. It's measured in percent. So it's really very basic stuff. So this one is just 1 star, and this guy is 5 stars, and n of 1 star. And the relative frequency is going to be measured in percentage points. That is simply the percentage number of 1-star hotels in our sample. What one typically does with those things, we build some kind of histograms. This is the simplest possible way how can we aggregate a univariate data with a picture without going deep into the background of those things. So in Germany, there are different types of schools. This is the basic school or press school. This is their translation to English. It's kind of very artificial for the things. Integrated school, junior high school, and so on and so forth. And what we get some kind of distribution of all the pupils in Germany over all those 8 types of schools. So on the vertical axis, you have a kind of either the percentage points or the absolute frequency. So in that case, it is in percentage points. So 35 means 35% of pupils go to the press school on the first years of school. Then we have gymnasium here. We have like 24% of pupils go to that type of school, and so on. So there are different ways to do that, and this is like the simplest one. You have here either absolute values or percentage points. You've definitely seen many other ways how can we show this kind of data. Very popular way of doing that is the pie chart. Actually, the pie chart was very popularized by Excel because we have very nice, colorful things here. But from statistical point of view, from the point of view of behavioral finance, pie chart or any 3-dimensional forms of the pie chart, they are not really reliable. Why? Because human eye is not really able to capture the differences in the squares as good as the differences in the heights. For example, here you would say Well, this thing is roughly twice as small as this part. Okay, so you can see with your eyes that this thing is roughly the half of that one. But it is difficult to say the same with pie charts, because actually what you have to do, you have to compare the squares, or you have to compare the angles. And with your eyes, you cannot really assess the angles in the same way as you can assess the length of something. So it's kind of a bit of misleading if you try to apply or visualize the frequencies in the pie charts. There are even worse ways to do that. Some try to model those frequencies with three-dimensional things, like some pyramids. So in that case, you have to assess the volume of something and say if the volume of something is twice the volume of something else. It's really impossible. So the simplest way, and really not a misleading way to visualize the frequencies, is going to be with histograms and not with some complicated things. So here we have the difference in angles, or the difference in squares, which is volumes in that case, which is difficult to assess. Now, another thing, so this is pretty popular. You can find histograms in newspapers wherever you want. But there's another one, another way of modeling, of characterizing the data, which is more mathematical. It is actually more informative, but it is less popular just because it's kind of more complex. So one possible way, and statistically the correct way to characterize the data, is the empirical cumulative distribution function, denoted by f hat at the point x. So it is a function, so we need dependence on the variable x. And what it does is simply counts the observations which are smaller than the predefined value of x. So f hat at the point x is simply the relative number of observations xi which are smaller or equal to the given value x. So I is an indicator function. It takes two values, either 1 or 0. 1 if this thing is fulfilled, and 0 if this thing is not fulfilled. So we have this indicator function in times. So if xi is smaller than x, and it is equal to 0. So, say we have a new movie, whichever, I don't know what was the last popular movie, Endgame, and you ask like, how many 10 persons, what do they think about the movie? So Endgame, it would be probably very improbable that the Endgame would get this kind of grades, but assume that it's some less popular movie with Schwarzenegger or whoever. So two guys say, well, it is pretty poor movie with 1-1, and one guy was really super happy about that. So what we do, we take our value x, let it run from 0 to plus infinity, and count the fraction of observations which are smaller than the given value of x. So imagine we take 1.5. So x is equal to 1.5. We have two observations which are smaller than 1.5. It means that our function takes the values of 2 divided on the sample size, it is 10, equal to 0.2. So 1.5, our function is equal to 0.2. If you take 1.6, you still have two guys which ranked, or who ranked the movie of less than 1.6. We are still by 0.5. And up to 1,99999, you will still have two guys who rank the movie with 1. So the function is intent locally constant from 1, from the smallest value up to 2. At 2 you have a jump, so if you are at 2.1 you have already 5 guys who rank the movie less than 2.1, and our empirical distribution function jumps to 0.5. And so on and so forth, so the only value of x, you will get some value of the function, and this function characterizes the distribution of the fraction of the people who rank the movie in their respective way. So what we will say, if you are somewhere here, This would imply that 90% of the people, so the function is equal to 0.9, rank the movie 4.5 or worse. So from a semantical point of view, those who had a lot of math during university studies know that it's not a very nice function. It is not smooth, so it has some jumps. It is locally constant function. And also from a semantical point of view, it is not, so this function is continuous from the right, but not continuous from the left. So at this point, the function has a jump, and it takes the value up there. So semantically, it's not really nice function, it's not differentiable, and so on and so forth, and those local points, but it has a nice economic interpretation. So this is like mathematical summary of the properties. The function lies always between 0 and 1. Why? It starts at 0 because it is the fraction, and the fraction can start with 0, so no single person ranked the movie less than 1, for example. And it ends up with 1 because no one ranked the movie with a grade which is higher than 5. So it is a kind of like probability. So it takes values always from 0 to 1. It's always increasing because if we increase our x, we increase this interval here, and more people are falling into that interval, and it implies that the sum is getting larger and the fraction is getting larger. So always, if you increase your x, you have more and more people who rank the movie less than the corresponding value of x. The sum increases, the fraction increases, and the fraction increases. And what we discussed already, that it is continuous from the right, and the relative frequency of xi is simply the size of the jump. So the important thing is that our empirical cumulative distribution function, which we'll discuss later on in more theoretical, from a more theoretical point of view, contains all the information about the sample. So in fact, you can retrieve the whole sample from your empirical distribution function. If you know this function, you can get back your data sample as it was. So it is a way to aggregate the function, aggregate the data, but you can also retrieve the data back from the empirical distribution function. Why? Because it's a kind of bijective relationship between the data and the function. It's a unique relationship between the data sample and your empirical cumulative distribution function. So there is no information loss in some sense, and if you have the function, you can retrieve your data, regardless how big your data is, because every point here, every jump in your function corresponds to a single observation in the data set. So for each loss, it is in fact nice. You aggregate a huge data set to a single picture, and you can get it back if you have the function form of the function. So, histogram. What we have here, it's a kind of frequency distribution. We have different schools, and every bar here corresponds to one of the school types. What we plot either frequencies or their actual values of those frequencies. Sometimes we don't have such nice type of data. Say if you talk about prices or age, there are very many different values. It means we cannot plot a bar for every single observation in our data set, but we have to aggregate these data in some sense or in some way. And that's exactly what is done by histogram. So imagine that we have some kind of strange data. We have an example later on with returns. So let's do it with returns. Return of some asset. I learned that returns in Ukrainian is dohini. I didn't knew that like 20 years ago. And returns can take, in fact, any values. It can take like minus 50% if you lose like half of your assets or half of your wealth, or it can be like 200% if you earn like double what you had before. So in fact, their asset returns can take any values between like minus 100 if you lose everything up to, in fact, infinity. So you cannot plot a frequency distribution for this infinite number of possible values, because what you will get, in fact, you will get something like bar, 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 then you have more dense bar, and then bars again, because every single observation will arise just once there. So what you have to do, you have to group the observations, and that's exactly what happens if you plot a histogram. We build some kind of, now let's do it here. So imagine that we have that's your time scale, and here is your return. Here you have 0. So in the last, say, months, we had once a very bad month, we had like very negative return of minus 4%. Then we had a couple of relatively bad months where we had a small negative return like minus 0.1 and up to 0.5. And then we had a couple of months where we did nothing, the return was 0, and we are lucky to have a couple of months where it's very high return. So what you do with your frequency, you will just say you have 1 month minus 4, 1 month here, 1 month there, 1 month there, 1 month there, and so on and so forth. So this distribution is not really reasonable, you cannot learn anything from that. So what people look then, they look not at the height of those bars, but they look at the density of those bars. So here we have just 1 bar. So it's very rare that we have a return which is so far away from 0. This is pretty dense. So there are many bars together. Here it's less dense, so more sparse. And we have some extreme positive return over there, with some very real event. So what people do, they look at the density and they plot the corresponding bars. So how we do that? We split our possible return into classes, preferably of the same size. And you count the observations falling into every single class. So here we have just 1 observation, here we have 0 observations, here we have 3 observations, 2 observations, 2, 1, and 1. And those things are plotted afterwards. So what we get, we had, to change color here. So we have a small bar over here. We have no bar over here. We have a bigger bar over there. We have average bar over here, average bar over here, and we have like that. So you know what there. So we aggregate the data to some classes and plot the frequencies, the class frequencies of their corresponding observations of the corresponding classes. So in fact, what happens? You fix some starting point. So we have to start the bars somewhere. Let's say we start them over here. And then you build classes around this x0 of length h. So you go to the right with length h of interval of length h, and you go to the left and to the right with the same length. So this guy is of length h, this guy is of length h, and so on and so forth. What you do, you compute their class frequency, nkj. So the frequency of the first class is 1. We have just one observation point, there is 0, and so on and so forth. Then we compute in exactly the same way the relative class frequencies. Those guys are measured in percentage points. And you plot, in fact, your fj, which is normalized by the number of observations and by the width of the class h. So at the end, you get f hat h, and you plot this. So f hat h, it is the functional form of this dual CQ. Now, seems to be simple, but there is a whole theory how to build a nice histogram. You of course don't know what exactly happens in Python. If you apply the function density, you just get your histogram. But in fact, there is a lot of theory how to determine this h. Because h is really very important for the form of your histogram. So let's have a look at those pictures here. So I took the Dow Jones index returns. Dow Jones is like a financial index for the 30 largest US companies. Pick the returns for the last couple of years, and I pick this h equal to 001, so I take very tiny intervals, up to 005, it is a huge interval. And for those 4 different ages, we have 4 different histograms. They look completely different. So here it is clearly very spiky. So it is very similar, in fact, to our bars over here. So the histogram here is clearly undersmoothed. It is not smooth enough so that we can see the true distribution of the data. We increase our age, we get something like this. It's already better. It's already better, but we have some strange spikes over there. So I personally don't know why we have a return between 0 and minus something less frequently than a little bit positive return, much less frequently than a little bit negative return. That's a kind of strange. If we increase age further, 001, we get a picture like this one. So it looks already more or less nice. There are no abrupt changes. It is more or less nice histogram. If we increase age even further, you get a histogram like that. You cannot really learn anything from that. It is a clearly oversmoothed form of data. So choice of age is really important, and there are many different ways how to determine age in some optimal way. So it is bad to have age too small. It is bad to have age too large. So there should be some intermediate value of age, which has some or leads to some nice properties of our history. So this is one parameter, and the second parameter is our x0. Where do we start our bars in the histogram? And the impact of x0 is seen here. So we have in all 4 pictures the same bandwidth age. 004, I don't change the values. It is the same data set. What I change is x0. So once it is 0, so we start building our bars from 0. 1, 001, 002, and 003. So you see the first bar here starts at 0. Here the first bar starts at 0.1, 0.1. This is 0.2, and this is 0.3. So red like that. The histogram look completely different. This is a kind of symmetric. They are roughly the same number of values which are to the left of the 0 and to the right of 0. This is a kind of symmetric, but the central part is much higher than the neighboring bars compared to that one. And those two, they look asymmetric. So here it seems to me that we have more observations which are smaller than 0, much more than to the right of 0. And here is the other way around. But the problem is it is the same data set. It is the same bandwidth. That it is possible to present the data in 4 completely different ways, with completely different inferences and with completely different economic interpretation of the things. So one should be careful with just calibrating the parameters. So if you don't know what h does and what x0 does, you can simply take or get the wrong inferences from the data or wrong interpretation of the data. So from that one would say, well, on average we do pretty well because in most of the cases we have profit or return which is slightly positive. We are doing a great job. if you show your boss this kind of the picture of the sales or the profits of the last month, you will say, well, in most of the cases we have something negative that cannot be true, but in fact the data is the same. So knowing the parameters in any model, even in such a simple model as our histogram, is crucial for understanding what happened there. So let's go further. This is like mathematical aspect of that. Hope you check those things. Now let's come to the parameters or to the characteristics of the data set. So in statistics, there are two main classes of the parameters. Those are the location measures and the dispersion measures. Location measures, they give you some feeling what happens with the center of the data, what is the most frequent observation, or what is the most popular observation. And the dispersion measures, they tell you how much the data varies around the center. So let's have a look at their possible things. The mean, it is the simplest one, but there are many others which in most of the cases are easier to interpret, and they are, or they have better properties from statistical point of view. And there are also different dispersion measures. Variance is not the most popular one, but depending on the application, you might have some kind of, let's say, other forms or other ways to measure the variance. So let us start with their location things. Something from the Lord of the Rings. The elves and dwarves, they have to earn something. So assume that elves earn so much per month. The average income of every elf is 2,555, and the dwarves earn a little bit less because they are afraid of all the possible bad guys, and they earn on average 12155. So if you put it on the picture, just without looking at the picture here, just by looking here, you'll say, well, elves, they earn really more than the orcs. Just by looking at the numbers, it's like 400 difference between the numbers. If you look at the picture, well, we see that the whole sample is a kind of shifted to the right, but there is a huge overlapping between the observations. Yeah. There is, of course, one guy, one elf who earns really a lot, and there is one orc who earns really little. But in fact, there is a big overlap between the two samples. So by looking at those two numbers, you cannot really infer that every single elf earns more than every single orc. That's a nice example in the spirit of this factfulness book I said at the very beginning. So if one says that in Germany one earns much more than in Greece, for example, it doesn't mean that every single German person earns more than every single Greek person. So on average, here you have an example. There might be some guys who earn a lot, but there are also other guys in other countries who earn as much as the guys in the first country. So this is like the average and the danger of pure looking at those averages. This is the formula, simplest possible thing, either for original data or for the classified data. That's simple. Now, important thing over here. So no one really thinks about the properties of the mean, but here I would like to show you why the mean is so important and why the formula like this is so important. So this kind of formula, those who did already some kind of data science know already. In most of the cases, if you try to make some forecast or you try to model something, usually you try to minimize your squared error. So this is your observation, this is your forecast for the model. Typically, this kind of function is your loss function. xi minus something, forecast for the model, squared, and sum up. Squared, because you don't want to have, you want to treat the underestimation and overestimation the same way. So we want to get rid of the sign. And you sum up because you want to look how your model works for every single observation. And you also know that you want to have this thing as small as possible because you want to minimize the forecast error of your model, for example. And in fact, the A which minimizes this function here, purely mathematically, is nothing else than the mean. So in fact, what you try to do if you don't have any further features, any other variables, the best thing what you can do while trying to minimize your forecast error, squared error, is just take the mean. It's going to be the best way to proceed from statistical point of view. Of course, if you have some features, here is going to be some function. It's not going to be that simple, but if you have just 100 numbers and you want to make some forecast, the best way is just to take the mean. It's mathematically justified by this formula. The problem with the mean, like this is nice thing, the problem with the mean are their outliers. It's extremely sensitive outliers. Imagine there are 4 guys working for whatever, what do we have, some big company, for Google. 2 guys earn just 1,000, let's say cubic, and a guy earns 10,000 cubic. What we say, let's compute the average salary of those guys. And the average salary of those guys is going to be 3250. Now imagine that the guys don't know the salaries of each other. You go to them and say, well, in your group of 4, the average salary is 3250. You can realize what is the feeling of this first guy. Well, come on guys, I get just 1/3 of what the average in our team is. And this guy is going to be pretty proud. So, mean is extremely sensitive to the outliers. If you have someone in the team or an observation in their data set which is completely different from the rest, like an outlier, their method of detecting those outliers, then it really shifts your mean in the wrong direction. The second thing that the mean, or the consequence of that, is that the mean is useful and reliable only for symmetric data. If the data is extremely asymmetric, this is a kind of an asymmetric data, because they have very strong right tail, they have an outlier on the right-hand side of the data set, then the mean becomes difficult to interpret. So let's have a look at the 2 pictures, very popular pictures. This is like a symmetric distribution. You see that the histogram is very symmetric. That's what we typically get, say, for financial data. If you take returns, if you recall those histograms for their Dow Jones returns, typically they look symmetric, or more or less symmetric. In that case, it's pretty easy to say that the center of your data set, like the location measure, is just in the middle. Now imagine that we have an asymmetric data, like this one. This kind of distribution is very typical for data which is always positive, for example, income. The income data looks always like that. Why? Because income cannot go into negative values, so it is like truncated on the left-hand side. Most of the people earn something in the lower part of the distribution, and there are a few of rich guys so that their right tail of the distribution is very long. So it is a typical form of typical distribution of a variable which takes only positive values. Also like prices, they will also have this kind of distribution if you have like a basket of very different products. Or some risk measures, if you take some risk of different products, it will typically be something like that. So, like distribution of income. And in that case, it is not clear what do you take at the center of the sample. Is the center this one, because it is the highest one, or is the sample somewhere in between there? It's not really clear, and that's why we have different locations measures which go beyond the classical mean, and they look like more precisely at the distribution of the data. The same on the left-hand side. This kind of skewness happens here not that often or that frequently, but still there are some kinds of data where we have the left skewed distribution. Now the question is, how can you measure the location of this kind of data? Here we have mean, it's fine for us. What happens here? One possibility is to take the trimmed mean. What happens with the trimmed mean? We just cut alpha% of the observations away from the data set. Alpha on the left-hand side and alpha on the right-hand side. So in fact, what happens? We cut off 5% here, we cut off 5% there, and compute the mean only for the center. This thing will profit, because we'll drop this guy from the sample, we'll drop that guy from the sample, and the average is going to be 1/1000. It's a kind of exaggerated, but at least we get rid of this rich guy in the sample. Why do we do that? So in fact, we get rid of extremes, and those extremes, in most of the cases in real data sets, there are some typos. Someone is sleeping on the keyboard, and there are too many zeros or too few zeros, and something is wrong. So just to get a twin, it's very elegant way to get rid of those extreme values close by someone falling asleep. So typical typos. It is the mean for the central 100 minus 2 alpha % of observations. Like the central 90% of the observations, because we dropped the first 5% and the last 5%. Most of the functions in software, statistical software packages, they have this kind of training where it's also easy to implement. Now, this is one possibility, and now the most popular alternative to the mean are the quantiles, or the median in some sense. The formula is a kind of messy, but I'll just try to explain you what does it do in the imagine what happens. We have our axis with the observations. We have some guys here. We have some guys here. So what quantiles do? They just cut the data into quarters in some sense. The median is going to be somewhere here. And median tells us that roughly 50% of the observations are smaller. And 50% are larger. So we just order the data from the poorest guy to the richest guy. You know roughly that we have, say, 1,000 observations. You go to the guy number 500, and his salary or his income just splits the sample into two roughly equal parts. Why it is robust to outliers? Because we don't look at the values. We don't care how much this guy earns, and we don't care how much that guy earns. What is important here is just the order. So we order the data from the poorest one to the richest one, and pick up the guy which is in the middle. The true values are irrelevant for the position. What is important is just the location of that observation in the whole sample. For quartiles, it's the same. So here is like our lower quartile, like 25% of poorest guys. And on the right-hand side, we have somewhere here, say, the upper quartile. We have 25% of the richest guys. So it gives you some feeling. How much should you earn to belong to the 25% of the poorest, or how much should you earn to belong to the 25% of the richest? Doesn't depend on the true values. It depends only on the ordering of the data. We'll have a simple example. So if we take our guys with 1,000, 1,000, and 1,000, and 10,000, then the median is going to be just between those two observations is going to be 1,000. So the median is 1,000. Doesn't matter how much this guy earns. He can earn 10,000, he can earn 1 million per week. The median remains the same, so it is completely not sensitive to the number of zeros the last guy earns. So it is really insensitive to any outliers. It's a very robust measure of the centrality of the data in some sense. We can compute those quantiles for any values of p. So here we have p like 50%, 50% to the left, 50% to the right, 25, 25 to the left, 75 to the right, and here 75 to the left and 25 to the right. We can do it, of course, for any value of p. Like p can be any quantile from 1%, say, to 99%, depends on the sample size. So let's come shortly to the picture we had over here. I don't know if you can see that, but we have X bar in this sample over here. So if you simply compute the average, then this is this guy, and this is a median. So this implies that 50% of the observations, they are smaller than this value, and 50% they are larger than that value. And here, and 50% on the other side. So, mathematically, there is a relationship between our quantiles and the empirical distribution function. So, the empirical distribution function will be step function. And there is, in fact, one-to-one relationship, say roughly one-to-one relationship between the inverse of that empirical distribution function and our quantile over there, but we'll have a closer look at that later when we talk about random variables. So this is our empirical cumulative distribution. We've gone through the properties. I will just have a look at this formula here. It's similar to what we had for the mean. So sometimes you take the squared error, like forecast, true value minus forecast. Some people take the absolute value. So if you take the absolute value here, then the best thing what you can use to forecast your xi is the median. But the median actually minimizes the absolute, the mean absolute error of your value. So the median has also a kind of reasonable mathematical property in terms of forecasting and in terms of performance measure of any forecasting tool for interval scale variance.
So may I ask a question? Does it mean so for asymmetric data better to use not a quadratic function as an absolute function? Or it is too bold conclusion?
Imagine, let's have a look. You have some, you try to forecast something, and here's your forecast error. So here's 0. Here you have perfect forecast. Like forecast error, let's write yi minus yi hat. So you take true observation minus your forecast. Here we have perfect forecast. Then you have big number over here. Then you have a small number over here. Small number there and small number there. So in this case, we have a large forecast error. It means you heavily underestimated the true value. So now imagine what happens if you, let's put some values here. Here it is 10. You misspecified your sales, for example, for 10 units, and here is just 1. If you compute their squared forecast error, you have 10 squared plus 1 squared plus 1 squared plus 1 squared. This 10 squared, it contributes a lot to your forecast. Because you're squared, so you have just 100 plus 1, plus 1, plus 1, plus 1. If you take the absolute values, contributes much less. So you have this 10 plus 1 plus 1 plus 1. So the distinction between squared and non-squares in the first step is how do you want to penalize your forecast errors. If you want to have such a model where the big forecast errors have to be penalized a lot because you just want to avoid misspecified demand for some product, then it's better to take the squared errors. If you don't really care about such big misspecification, but you want to have it on average pretty good, then it's better to take the absolute values. So this is the first economic difference between the squares and non-squares. From the point of view of symmetric asymmetric, now imagine that we have a point somewhere here. So you have heavy overestimation of your forecast, so this thing is heavily negative, so you have overestimated yourself, the sales. So we have this one and this one guy. In fact, you treat them in the same way. So they contribute exactly in the same way to the positive or to the negative. So the difference is in fact just in treatment of the extreme specifications. So that's the propagation. So there's just not only mean, which is used by everyone, there are also some other types of location measures like medians, quantiles, and so on. Now let's come to the dispersion or variability of the data. We have histograms. They look very differently, but if you try to characterize every single data set here just by the location measure, they are the same. So first, they are symmetric, so we don't care if you take the mean or the median. The center is here at 0, the center is here at 0, and the center is here at 0. So if you look just at the means or the medians, you don't see any difference between the observations, between the samples. They are going to be identical. Yeah? Just imagine you don't plot anything, you have your Excel sheet and you compute their mean at the very bottom. The numbers are the same, you compute the data sets are the same. But in fact, there is a difference in the samples, and it is characterized by their variability of the data. There are some guys just going to -3. Here we have guys going to -5, and here we have guys only between -2 and 2. So the question is, how do we quantify this variability of the data? Again, there are plenty of different measures. Some people, depends on the application, of course, but some people just are happy of using their range. So they take the largest value, they take the smallest value, the difference between them tells them the interval or the length of the interval where the whole sample lies. Take maximum, we take minimum, take the difference, and the difference is the length of the interval where their sample lies. If the difference is small, then the sample is very concentrated. If this difference is large, it means we have very large dispersion of the data. The problem is, of course, that those things are typically typos, that this is the largest value and the smallest value. So you quantify your variability measure by looking at some typos or by looking at the extreme values. So there are some situations where it's fine, but in most of the cases, especially in larger data samples, it's not really a reliable measure of quantification. The second thing is their interquartile range. Interquartile range relies on our quartiles. That's what we have over here. Like this is the guy which truncates the lower 25% of the data and the guy which truncates the upper 25% of the data. And the difference between those two guys is our interquartile range. So it is similar to our range, but it looks not at the extremes, but it looks at the quartiles. So in fact, within this interval of length QA, we have 50% of the central data, of typical data. So interpretation is that in an interval of this length here, we have the 50% of most typical and central observations in the data. It is robust to outliers because we've got reach from these observations here and those observations here, and we look at the most typical observations. So what really happens to our central part of the data. It is related again to the quantiles and quartiles we have. Later on, we will see an example with the box plot, how it is used for visualization of the data. And of course, the most popular way to measure the volatility and variability of the data is the sample variance or the empirical variance. You simply take all the xi, subtract the mean and the location area squared, sum up and divide on the sample size. There are formulas for the classified data. This is the absolute frequency, this is the relative frequency, but this is like their most popular way of doing that. In the literature, we have sometimes this formula with n, because we have n summations here, and sometimes we have the formula with n-1. We'll discuss it later on, but this is related to their number of degrees of freedom and to their maximum likelihood estimation of that parameter. So there are two different formulas, and typically you can say in software what kind of formula you want to use. Of course, if any slides, you don't really care about that. So if you have 1,000 observations, it doesn't really matter if you divide it over 1,000 or 999. But for smaller samples, it is software. The problem with this thing is, of course, there are units. Say you analyze the prices, and you want to measure the variability in the prices. So you do something, but you square it. It means that their S squared at the end is measured in euros squared, in dollars squared, in hryvnia squared. It's not really interpretable, so what we will do to get rid of the squares, they take the square root. So the square root of this value here is the empirical standard deviation or the sample standard deviation, and it is measured in the same units as the original data. The interpretation is difficult because say with the mean, it is trivial. So the average income is, say, 1,000. It means that on average, every single person in your data set earns 1,000 per month or per term. In the variance, it is, let's say, if S squared is 10,000, then S is 100. So 100, it is the square root of the average quadratic deviation from the mean. So economically, it's difficult to interpret what it is. So people usually don't look at, do not try to interpret the value of their volatility measures or variance measures, but simply try to compare those S's with other S's for different samples, for different models. Because the value itself has no economic meaning. You just compute some price differences or income differences, then you square them to compute the mean and so on and so forth, and then take the square root of the value. So economical interpretation of those things is really difficult. In contrary to that one is going to be easier because you have those quartiles. Quartiles are measured in euros, and you know in which interval measured in euros most of the incomes are lying. But here it's kind of tricky. Then we have also, we have to make a break at some point. Perfect timing, more or less. Now, visually you can say this histogram here is symmetric, those two are asymmetric. If you have like 1,000 variables or 1,000 features in your data set, you cannot look at every single histogram and say, well, this is symmetric, let's take mean, this is asymmetric, let's take median. You need some quantification measure for your symmetry or asymmetry. And one possibility to quantify the symmetry of asymmetry is the so-called skewness, or empirical skewness. It is a measure of symmetry of the data, and is computed, in fact, in a very similar way as we do it with the variance. So in the variance, we have xi minus mean squared. Here we don't take squared, but we take to the power 3. So just again, this one, it looks exactly like our variance, sample variance, but we take it to the power 3. Why do we take it to the power 3? It's like what we go to different pages. That's what we have done here. If you have very large value, very large white tail, then the quantity will be taken to the power 3. It will contribute a lot to the sum, and our sample screws will get larger. So this power 3 simply penalizes large values, large deviations from the mean, much heavily than it is done in the variance, and positive and negative things are penalized in different ways. So positive deviations will be penalized with plus, and negative deviations will be penalized with minus, because we have an odd power. And now the aggregation of all those location aggregation measures is the so-called box plot. I don't know how in Ukrainian newspapers and journals, but in German or in European journals, it is nowadays very popular to show some box plots of income, of rent prices, of ages, of and so on and so forth. So they have those box plots everywhere. I don't know if the readers really understand what those box plots mean. They have usually some small legend below the picture, but it's really like kind of tricky. But what the box plot consists of are our medians, quartiles, interquartile ranges, and so on and so forth. So this bar typically is the median. So it splits our data set in the upper half and in the lower half. Like 50 guys, 50% of guys are here, 50% of guys are there. Then those two bars here are our lower quartile range and lower quartile and upper quartile. So 20% of 25% of guys are here and 25% of guys are there. So this distance here is going to be our quartile range. So the height of the rectangle here is our quartile range, our dispersion measure. This is our location measure, this is our dispersion measure. Then we take also, or at least in R, this is the implementation how it is done in R, we have the not outliers in some sense. So we take the upper quartile and add something what is proportional to our quartile range. And then we have extreme outliers and the largest and the smallest value. So the guys up there are typically treated as outliers and either have to be eliminated from the data or something else has to be done to get rid of them. Now, why it is useful to look at the box plots, because in Python or in those in gplot package, there are also those wiring plot. There are all possible ways to do that, but box plot is like the basic idea of the wiring plot or other forms of plots. Because in fact, you can say something about the skewness and the distribution in general. Say if you have income, this is let's write it on the horizontal axis. They make most of the examples with income because it is I read that Google is working on some kind of mind reading apps. They bought a company who tried to reach their the thoughts in some sense. That would be very applicable here. So I went to write so the switch to the company. So here is 0, is Bill Gates. So typically the picture for the income is going to look like that. That's here, and this is Bill Gates. And here's some guy. It's not linking. So this would imply that we have very skewed data. In this area, starting from the median here, we have 50% of the poorest. And up there are the 50% of the richest. So the poorest, they are really concentrated in this bar here. So here we have 25% of the guys who are just 25% of the richest among the poorest in some sense. Of the richest from the poorer part. And they are really concentrated. Very communistic way of life. Here we have a more spread because those are guys who earn more and a small variation in the data. And we go up to here, and those are the extremely rich guys who earn a lot. So we can really read pretty much from this kind of data. You can also have something symmetric, but if it is symmetric, you cannot make some economic stories out of it.
Excuse me.
Yeah.
May I ask a question? Why these lines, like this upper fence and lower fence, are asymmetrical if we add in and subscribe the same like interquartile range?
It's a good point.
What actually? No, it's like
For me, they're not symmetric. The most
Well,
one is
on the picture, the asymptotic, I think the formula is wrong. I think we take 1.5. It's not really quartile range, it is I have to check those one. So something is wrong here. You're right. Those should be. So this is the correct picture, but they're wrong annotation of the things. Something is. Yeah.
Just wanted to ask about whether we can just measure the degree of skewness by subtracting median from the mean, and why should we use that cubic skewness formula? Maybe it has some nice properties.
Yeah, as a skewness measure, you can take this difference minus that difference. If the two differences are the same, then you have like a non-product. Why skewness is typically used? Because those things are thought as so-called moments of the data. Mean is the first moment, variance is the second moment, plus the second power, and you have the third power here is the third moment. There is also a measure of the tails, the measure of the extremeness of the data. Especially if you take financial data, then you have very long tails. If you have some crisis, then you have very negative returns. If you have very nice periods, like Trump is de-elected or some sense, and you have very nice periods and you have very positive returns. So the question is how to measure the handiness of the tails, and then you put the power 4 here, because the extreme way we shall penalize you. But this is like, I have never seen that, as you suggested, but theoretically it is possible just to look at the difference of those things. So this is like the end of the first part, and let's make a break and then 15 minutes, so quarter to do, and then proceed with their characterization of the binary. So, shall we start? Let's talk a little bit about binary data, because everything what we have seen so far, it was just for one sample. So we have some sales and we have some incomes, but it's just one-dimensional data set. Typically, you don't have one-dimensional data set, but you have many different features, many different variables, and you want to model how they are related together and what kind of impact one feature has on another feature. So assume that we have two variables, just for simplicity, x and y, and we have pairs. So this is their, say, grade in linear algebra for one person, and this is the grade in statistics for the second person. So we have one person, and this person is characterized by two different measures, grade in statistics and grade in linear algebra. And the same for the last one. So for every single variable, we can compute everything what we have done so far. So we can compute the average grading statistic, we can compute the standard deviation of the grading statistics, we can plot the histogram, whatever you want. The same we can do for y. So we can compute the average grade in algebra, we can compute the standard deviation of that, make some pictures, and so on and so forth. It's not interesting because we can apply everything what we have seen on the previous slides. The question is, how can we quantify, how can we measure the relationship between x and y? So let's have a look at the pictures. The easiest way to do that is just to plot the data. So on the horizontal axis, we have the observations for x, and on the vertical axis, we have the observations for y. This kind of picture is typically called the scatter plot. The two pictures, they show very different ways their variables, the features can be related to each other. Here they are just randomly spread over the whole square, so there is no clear relationship between x and y. What do I mean? There is no clear relationship. Say if x is somewhere here, we cannot say what kind of value y is going to take. So y can take, in fact, any values from the highest one to the lowest. If x is somewhere here, again, we have the whole spectrum of possible values of y, and the same if x is here. So it's really spread all around their possible values of y. Here, we clearly see there is some relationship. If x is large, then y tends to be large as well. If x is small, then y tends to be small too. So there is a clear component between the values for x and the values for y. Here it's also like a straight line, but it should not necessarily be a straight. Here we have an inverse relationship. Large values of x go together with small values of y, and small values of x they go with large values of y. So here we have a clear relationship between x and y. Here too, but here we don't see visually any special pattern in the data. Now pictures are nice, but the question is how can we? It's three-dimensional. I don't know what that's like. You can also try to do the same in a three-dimensional setting. So here we have like x, y, and z. You make the plots, so the red plots are their individual observations for everything per triangle. So you have great in statistics, great in algebra, and great in whatever in analysis. And every single point uniquely specifies all your 3 points. Now the projection on the surface here, on the horizontal plane here, implies that we just take vertical points of every single red dot and project it down. It means we eliminate the impact of the vertical axis, just press everything on a single space. And the picture over there, it's when we project all points on that plane, so we fix the value of x1, and everything is projected on their vertical plane there. Now the problem is that already here it is difficult to see something. Like most of the software packages, they allow you to rotate this cube, so you can see the scatter plot from all possible perspectives and learn something from that. But if you have more than 3 variables, all those things become impossible. So you cannot really visualize a 4-dimensional scatter plot in a normal natural way. So of course you can do some projections, but they are not informed. But those rotating cubes, they are really cool. So the question is, how can we quantify this relationship? And the simplest way to do that is with empirical covariance. Important is that our x and y's, they must have interval scale. In most of the cases, this implies that you cannot compute this covariance, say, for the stars. If you take hotels or if you take grades on Amazon, you cannot take those stars and plug into this formula. This formula of the empirical covariance in general is used to quantify the relationship between interval scaled variables. Now, what their formula looks like, we have the same sum and 1 divided on that in front of it. Here we have the deviation xi minus h bar, so the deviation between their grade in statistics from the average grade in statistics times the grade in algebra minus the average grade in algebra. You sum all those things up over all students from 1 to n and divide it on the sample size. As before with the variance, sometimes we have the formula with 1 divided on n, and sometimes we have a formula with 1 divided on n minus 1, but we'll discuss it a little bit later. Now, yeah.
Why aren't we squaring it or having an absolute value of that? Yeah.
That's what I will explain here. So why the formula looks in such a strange way. So for variance we had squared, so we had something in here. Now let us see what happens with our points. So assume that we have those black points here, and let's pick up these guys. So for this guy here, x minus mean, so this is the mean for x, this is the mean for y. For this guy, xi minus x mean is going to be positive. Yi minus y mean is also going to be positive. Which means this product here is going to be positive because each element is positive. Each element is positive. So this thing here, it is yi minus y bar. This thing is xi minus x bar. This guy is positive, this guy is positive, and the product is positive. But this guy is other way around. So yi minus y bar is negative because it lies below the mean. X bar minus xi minus x bar is also negative because it lies to the left from the vertical line. It means that two things are negative, but the product is still positive. Yeah, so this one is yi minus y bar. This is this thing, and this is xi minus x bar. It's also negative. But the product is positive because we multiply to negative 6. Okay. Now here, we have one sink is negative, one positive, meaning the product is negative, and here's the same, it's other way around. For x's it is negative, for y's it is positive, but the product is not. So this implies that if in our sample most of the points are over here and over there, the sum is going to be positive. Because we accumulate more and more positive summands in the sum, and the result is going to be positive. If most of the points are over here, this would imply that most of the summands are negative, and the sum is going to be negative. So, in fact, we try to reflect in which quarter of your coordinate system the point lies with this product. So, it is here and there, always positive, here and there, it's always negative. So, if you come back to the previous slide, so if you just take the averages, most of the points are here and there, it means the sum is going to be largely positive. So the sum of this xi minus x bar times yi minus y bar is going to be much larger than 0. And here it's other way around. The sum is going to be much less than 0, because most of the points are in the upper part and in the lower part. So in fact, this strange formula actually captures the location of the points in those 4 quarters. And we can just try to do something. Of course, it's going to be measured in grade squared or in euro squared. It's not really interpretable, but there are ways how to normalize and how to standardize. But the formula itself, it actually helps you to capture the location of the points in their coordinate system. What's going to be here? Here, if we put the average for x and for y, there would be some positives, there would be some negatives, but in the sum, they will probably cancel out, and the sum is going to be roughly equal to 0. So that's like motivation why the formula looks like this and contains some other. This was the motivation. Now, some important properties. First, the formula is symmetric, which means if you take the formula and swap some things here, nothing changes. So it means it makes no difference if you measure covariance between x and y or between y and x. So if you rotate your grade in statistics and algebra, nothing is going to change. So this is an important property. So it is directional. So that's why it's symmetric measure of dependence. You can change the variables, but nothing. So there is no directional dependence in this measure, but just general dependence between x and y. Now it is invariant to shifts in location. What does it mean? It means if you take just our scatter plot, let's take this one and shift it somewhere. And I subtract 50 from every single observation, nothing is going to change. The shape of the pitch is going to remain as it is. That's important if you, for example, normalize some quantity. So you just subtract the poorest high from the sample and measure the dependence in the dependence of the income with respect to the poorest high. So shifting this thing doesn't change things. The scaling parameter, so if you multiply the things, would change the formula. So if you go from euros to 1,000 euros in a data set, say in the first Excel sheet you have everything in euros, huge numbers, you say, well, let us get rid of the 3 zeros, so we divide everything on 1,000. Then this will also change the covariance, because this multiplicity parameter here, A and C, they will arise here in front of our covariance. So it is not really nice to do it in that way. Now there's one property which relates here our covariance with the variances. So those are the two standard deviations for X and for Y separately. Those who had a lot of mathematics and analysis, they know something like Jensen inequality. So this property here comes from the Jensen inequality and tells us that our sample covariance is always smaller than the product of the two standard deviations. Why do we need that? We'll need it on the next slide. So we'll do it here. So it is sensitive to outliers. Why? Because the mean is sensitive to outliers. So we have outliers, then they will influence the mean here. And we also have the variance. It's something like the variance. We multiply deviation times deviation, so the whole formula is going to be sensitive to outliers. So before measuring any correlations, you should carefully have to look if you have some outliers in the data or not, because those outliers they really shift strongly their the dependence measure. So, for example, it might be the case that your data looks like this, and then you have one outlier over here. This outlier will force the formula to think that you have some kind of positive dependence between the data. Yep. So their means are going to look like that. There's one observation over here, so this element is positive, one observation, many observations are over here, and the sum of SX6 is going to be much larger than 0, just because of one single outlier. Without that outlier, you would have the means over here and over there, and the sum or SXY is going to be roughly equal to 0. So outliers, they heavily influence their correlation or dependence measures in this framework, just because they influence the means and simultaneously they are going to influence the covariance. So one problem is, of course, that variance is not normalized, it's measured in some strange units like squares or products of two different units. So one possibility to get rid of that is to compute the sample correlation coefficient of Pearson. This is the most popular correlation coefficient, and frequently when the people say about correlation, they need the correlation of Pearson. But we'll have two other correlation measures, so it is deliberately distinguished between the correlation of Pearson and other types of correlation. So what we do, we simply take our sample covariance or empirical covariance on the previous slide and divide it on two standard deviations. So this is the covariance. Now, why it is nice, we will see down here. First thing, it is symmetric. From the same property of our axis, if you okay the observations in our product, everything is fine. What is important? Invariant with respect to shifts and in their scale. So this part is important. If you change the scale of your data, like from euros to 1,000 euros, it will not change the correlation. Or if you switch their degrees from Fahrenheit to Celsius, it will not change the correlation. If you change the currency, for example, if you multiply your prices with the exchange rate of euro hryvnia or euro US dollar, it will not change the correlation. So it is a very nice property that the correlation does not depend on any shifts in the location and in the scale. So it means the correlation is insensitive to like prices in different currencies. in euros or in 1,000 euros, or in, say in Celsius or in Fahrenheit. You can transform your data linearly, which will not change the correlation between them. And probably the most important property of the correlation is that it is bounded by 1. So if you have a look at this formula, so this thing is always smaller than the product of 2. This would imply that this upper part is always smaller in absolute value than this part, and this would imply that the correlation is always smaller in absolute value than 1. This would imply automatically that the correlation is always between -1. Between -1 and 1, just from the Jensen's quote. Let's have a look what kind of extreme values you might have. Perfect correlation if perfect positive correlation if R is equal to +1. R equal to +1, which means that all observations they lie on a single straight line. The slope of the line is irrelevant, so it might be like splitting the angle in 2 parts, 45 degrees and 45 degrees line. It can be any other line, but the important thing that their points lie on a single line. So the same result would be if the line looks like this, looks like that. So the slope is irrelevant. The main point that every single point lies on a single line on a single straight line with positive slope, or with a negative slope if their correlation coefficient is equal to -1. Again, it doesn't really matter what kind of slope we have. The main thing is that all points lie on a single line with a positive or with a negative slope. So what does it imply? Here x large would imply y large. Here x large implies y small, and other way around. So there is no directional impact. You can take y small, x large, and so on. Now, if correlation coefficient is close to 0, so this is always positive, it is standard deviation, it cannot be equal to 0. So if this guy is 0, it means that this guy is 0. And you know that if this guy is 0, then our dots look like a circle, like a ball. That's what we have here. So if the correlation is big, close to 0, then most of the points are going to be like ball shape. Or we might have a strong correlation. We might have a strong correlation, so R in that case is, say, it's difficult to assess, but let's say it's -0.8. Minus, because we have a negative slope underlying the data, and it is 0.8 is pretty large because the points are pretty close to that line. The points come close to the line, so there is pretty strong relationship between x and u. Now, why do we talk about lines here? Why do we assume that our dots should lie on a straight line? Because our correlation coefficient is a measure of linear dependence between two variables. So it is really important. Correlation coefficient of Pearson is a measure of linear dependence between two variables. Now, why can it also be misleading to compute that correlation for other types of data? Let's take the following. So here we have 0, and let's take the lines, the dots which look like this. So let's assume that it is symmetric. It's not really symmetric on the picture, but we believe that it is symmetric. There is some dependence. So we see that there is some dependence. If x comes close to 0, then our y comes close. Our y comes close to 0. If x goes very positive, then our y increases. If x goes very negative, then our y increases again. So there is intuitively strong relationship, a very strong functional relationship between x and y. The problem is that if you take this data and compute the correlation coefficient, it's going to be 0, or at least close to 0. Why? Because there is no straight line which fits the relationship between x and y, and because R, our correlation coefficient of Pearson, is a measure of linear dependence. So if one variable increases by some unit, then we expect that our second variable will also increase by some unit. So it is correct to compute our correlation coefficient of Pearson only if we talk about the linear dependence between two variables. Here, we have a clear functional parabolic relationship between x and y, and our correlation coefficient, if you take real data, is going to be really close to 1. In terms of the regression analysis, if you try to draw a regression line here, it's going to be horizontal here. And this would imply that there is no linear relationship between x and y. So this linear here so if x by say 8 units by b units. So if A increases by so many units, then B increases by so many. So if I get like 5 centimeters taller, then my weight should increase, say, by 7 kilograms. So there is a linear relationship between body height and body weight. And this can be measured by the correlation coefficient. Now let's have a look at another correlation coefficient, which is nowadays or became extremely popular. I mean, jump to show you who did already some machine learning stuff. If you apply any type of machine learning, like any neural network, for example, then what you do is actually you try to model some nonlinear relationship between your output feature and your input feature. If you take, for example, multi-layer perceptron, and you take some linear activation function for some reason, everything collapses to linear regression. So everything what you do in machine learning, in fact, in such predictive machine learning supervised, is trying to capture some nonlinear dependencies. And this implies if you take your data and compute the correlation coefficient of Pearson, you look only at the linear dependence. And it has little to do with some complicated nonlinear models which you try to apply afterwards. So this linearity is really crucial. It's good if you do linear regression analysis afterwards, but if you do something different, then it's not really a good starting point to analyze the data. Now, another correlation measure is the correlation measure of Spearman. It can also be applied to ordinal data, but also for internal scale. So what this thing does, it works not with the observations, but with the ranks of the data. So let's try to understand what a rank means. So we have our data x1 to xn, whatever grades and statistics. We order them. This is the guy with the worst grade. This is the guy with the best grade. And what we say, or what we define by rank, we say that the rank of the grade of guy j with the grade xj is v, and this implies that this guy is on the least place in the ordered sample. So let's say we have 4 guys. They have 2, 5, 1, and 3. We order them. The first guy had the worst grade 1. Then the second guy had the second worst. This is the third one, and this is the fourth one, the best one. And we say that the rank of the first guy with 2 is actually 2, because because his grade is on the second place in the order itself. the rank of guy 2 is 5. That is the best guy. His place in the ordered sample is number 4. So his rank is 4. And the same for 3. This is the worst guy. He is on the first place in the ordered sample. So his rank is 1. And then for the fourth one, it's number 3. So in fact, you don't look at the true values, but you look at the position of that guy in the ordered sample. So you look only at the ranks, but not at the absolute values. So what we do then with those ranks? We take a formula which is very similar to our correlation coefficient of Pearson. So let's go quickly over here. So if you look at this formula here, it's xi minus x bar, yi minus y bar. What we have for the correlation coefficient of Spearman is exactly the same, but you replace your x's with the ranks. So what you do, you compute the correlation coefficient of Pearson, but not for the true data, original data, but for the ranks of that data. It's like Pearson for ranks. Those guys down there, those are the standard deviations of the rank. So you don't go deep into the details, but to give you just feeling that we compute the correlation coefficient of Pearson, but for the ranks and not for the original data. Now, what kind of consequence does it have? Assume that we have two, very unlike the data here. Okay, this correlation coefficient of Spearman is a measure of monotone dependence, not of linear dependence, but of monotone dependence. It implies we check if the relationship between x and y is monotone. What do I mean by that? Let's have a look at these red dots here. They lie on a monotone function, some x cubed or whatever. If you compute the correlation coefficient of Pearson, we'll get 9.8. So it's of course high, but it is not perfect in some sense, despite of the fact that the dots lie really very close to that cubic spline, or to the cubic function. If you compute the correlation coefficient of Pearson, we'll get something what is almost 1. So if you measure their monotone dependence between x and y, you get almost perfect dependence because the dots lie really on a monotone function. If you try to capture the linear dependence for those two variables, x and y, you get something which is rather far away from y. Another example, let's take a data set with an outlier. If you compute the correlation coefficient, we've seen before over here that if you have so this outlier will really shift the correlation coefficient because the means shift up and to the right. And despite that the dots lie really on a straight line, the correlation coefficient is going to be 66%, just because of this guy. As imagine we put the averages. There are plenty of the guys over here. Positive, there's one guy up there, and there are a few guys in the lower quartile, which means that the correlation coefficient will be pretty far away from 1, and in fact it's going to be 66%. It's pretty weak correlation, despite of the fact that all of the observations, excluding this one, rely on a straight line. Now, if you compute the correlation coefficient of Spearman, we don't look at the true values, we look only at their ranks. And in fact, it is a monotone function. It has simply a very strong jump up there. So it is a monotone function, so the correlation coefficient of Spearman will actually capture this correlation, this dependence in a very straightforward way, and we still have a correlation of Spearman which is almost 98%.
I have a question.
Yeah.
What would happen if you make a scatter plot with ranks of our data as x and y values? Would it be with the same kind of shape, or it would be more linear, or it doesn't matter at all?
in those cases, we're going to be on a straight line, because if the correlation coefficient, because what we do, we compute this Pearson for ranks. And if it is 1, the ranks should lie on a straight line.
Yes, so we are like straightening those. Oh, okay.
We transform the variables.
Okay,
So for this picture, we'll get x, this is Rxi, goes from 1 to n. And here it goes from 1 to n as well. So the point over here for the first observation, let's say this point here. It's Rx1, Rxt, okay, y1. What does it mean? This is the smallest x variable and the smallest y variable, or y observation. Which means that the smallest x comes always with the smallest y. And their point up here at the very top would imply that the largest x come always with the largest y. Which means the tallest guy is always the heaviest, the smallest guy is always the lightest one. So it would kind of go around a straight line, 45 degrees line. Yeah.
I have one more question. The picture with the outlier. So the Spearman correlation is not sensitive to that outlier, but if outlier will be located under the line, like somewhere down, like, do you understand?
Yeah.
Yeah,
mean
somewhere
somewhere
here. So will Spearman correlation
Figure out
It is positive if it lies on a monotonely increasing function, and it's going to be negative if it lies on a monotonely decreasing function.
but it will be like one of
If it is not. So in that case, it will not capture an outlier which goes down. So it really either monotonically increasing or monotonically decreasing. You cannot apply, for example, that one to this as well, because it is neither increasing nor decreasing. Yeah, I understand the problem. It would be, of course, perfect to have some measure which would quantify any kind of dependencies, like from the sine function or like something else, but it's difficult. So you need to model the relationship directly with some function and then try to work it out. So just to remember, this is Pearson. I don't know why we have this notation here. Pearson. This is also Pearson. So this was their second measure. Typically, if you compute the correlation, there is some kind of option in your correlation function which tells you I want to have the Spearman correlation or I want to have the diffusion correlation. There is also the third one, which is even more general. It is a Kendall-Style, but the formula is already kind of difficult to explain. So let's come now to a correlation measure for nominal variables. Say we have two characteristics, the gender, boys and girls, and they're passed or failed in an exam. In fact, if you have this kind of data, let's think what someone will do who doesn't know what is the scale of the variable. So we have to code it in some way. So let's say girls are ones, boys are zeros. Passed is 1, failed is 0. So the data will look like that. So we have a girl who passed, we have a boy who passed, and we have a girl who failed, and so on and so forth. So in fact, we coded our variables, boy, girl, our like qualitative variables with some numbers. Passed, failed is also 0, 1, and our data looks like this one. If you don't care about the scale, you would just put those numbers in any correlation coefficients in Pearson. Of course, you can do that, because you can compute the average of all those ones and zeros. You can take every single observation and sum it up and divide it on Sx and Sy. But this is not correct in some sense. Mathematically, you can do that, and your software will not actually know, will not say, no, it's not working, because mathematically you can compute that. But it is simply unreasonable because it is a measure of linear dependence. Here we don't have any linearity. Just imagine how the data looks like. The data consists of 4 points. So here is gender, here the exam. So here we have all girls who failed the exam. Here we have all boys who failed the exam, all girls who passed, all boys who passed. What kind of linear dependence do we try to capture with the Pearson correlation coefficient? It's really nonsense with this kind of data. So we cannot simply apply this kind of correlation measure to this type of the data. Many people don't care. They have some data set with many features. They compute all correlations as well. We got something, but just intuitively we cannot do that. So what we still can do is we can compute some kind of contingency table or frequency table, and then relying on this table, we can get some measure of dependence. So let's say we have a very good class. There are 84 boys who passed, 61 girls who passed, 9 boys failed, correct, and 2 girls who failed. So those are their marginal frequencies. We have altogether 93 boys. We have 63 girls, 145 passed the exam, and 11 failed the exam. We can divide everything on 156. So this is our n. But let's do it in, I think, more detail because. Okay, let's do it. So if this is our n, and if we divide every single value here over n, we'll get the same thing in percentage. So 60% of the sample are boys, 40% are girls, 93% failed, 7%, 93% passed, and 7% failed. So what we can do with that, we can first try to formalize this thing, and then we'll build a correlation method for that. So let us define and date some frequencies. So Nij, it is the absolute frequency of the pair AI and Bj. Say in our notation, N11. This is the number of, we have 1 girls passed the exam. So N11 is going to be this one. Yeah. That's not nice coding. That's what I change. So let's make it consistent with the table. Boys passed, it must be 1, 1. So boys are 1s, passed is 1, and girls failed, it must be 2, 2. So girls have 2, and failed is also 2. So the pairs are here like 1, 2, 2, 1, and so on. So we should replace all zeros with 2 here, and then it is correct, but the picture remains the same. We have 1 here and 2 here. So we have a new notation now. This is N11. And if the number of boys who passed the exam. And 2, the number of girls who failed the exam. Then we have their marginal frequency. That's what we have at the boundary. It's also simply the sums of what is on the left and what is on the right. So that's going to be n1 dot. It's going to be n2 dot. So 93. This is the number of boys and n2 number of girls. And the same is going to be one number of field. And then the 2 is number of past number of field. Yeah, so every single number can be interpreted in some reasonable column. In a general form, we can say that the table looks like that. Those are the possible outcomes for the variable x. Those are the possible outcomes for the variable y, like boys, girls, past, failed. In general, we can have many outcomes, like not just past and failed, but you can also have grades here, like 5, 4, 3, 1, and so on and so forth. You can split their pupils not in boys and girls, but in some classes, like their 1A, 2A, 2C, and so on and so forth. So there are many possibilities how to order the observations and consider the observations. Now, what kind of dependence do we expect here, and how can we quantify it? Imagine that our table looks like, imagine that our table looks like this one. So we have values of boys. It's really convenient. We have boys here, girls here, we have past, and we have failed. How the table should look like so that we have a perfect dependence between gender and pass or fail data. Imagine, do it politically correct, this kind of table. This kind of table, we have perfect dependence. All girls passed the exam, no single failed. And all boys failed the exam, no single boy passed it. So if the table looks like that, we have a perfect relationship between the gender and the grade. The table can also look differently, say boys, girls, pass, failed. 93, we take 46 here, 47 there. And we have 31 here and 32 there. It just wasn't defined. So we don't have any relationship between past, failed, and the gender. In fact, just by looking at the table and using the numbers appropriately would help you to quantify the strength of the dependence. We don't go into the motivation for the formula, but in fact the formula is very simple. You compare their values in the table, so those n, I, and j's are the absolute frequencies for the pair I and j, with the marginal frequencies and I dot and dot j divided on the scaled in appropriate way. And this chi-squared would actually tell you if there is some relationship between their outcomes for the variable x and the outcomes for the variable y. If this chi-squared is large, so take some large values, which means that this difference here is very large in some sense, and we have a kind of sign of dependency. Let's do it this way. That's what we observe. In the table. And that is what will be observed if the variables are independent. What would we observe if the data is independent? So in fact, we have here those marginal frequencies, and you see that those numbers here, they do coincide with other marginal frequency here. So what we have at the right hand side of the T. So in fact, we compare what we observe with what would we observe if the data is independent. So again, we have to square it, sum it up over all elements of the table, and we end up with some chi-squared. The problem is that this chi-squared is not normalized. So it takes no fixed value, say between -1 and 1. To do that, there is special type of corrected coefficient, the corrected contingency coefficient of Pearson. It is the C, which is computed this way. It is normalized by the maximum value, which is the minimum of rows and columns in the table, -1 divided on the minimum between rows and columns. And if you divide this C over C max, you have 0 and 1. So again, this normalized correlation coefficient takes values between 0 and 1. 0 implies that the variables are independent. 1 implies that the variables are dependent, like what we have in the upper part of the table over there. Important here is that we don't have any directional dependence. So we cannot say if one variable increases, the other one increases too, because the underlying scale is nominal, so there is no order in the data. I just write it up because you get the slide. So we cannot say that x increases if y increases too, because x and y have nominal scale. We cannot say what is better, what is worse. So we cannot say it's better to be a boy or it's better to be a girl. So the data is not ordered, and it implies that we cannot say x increases. Because if we say about increasing or decreasing, it means the data is ordered, and our data by default or by definition should not be ordered or should have nominal scale. So x and y. So this implies we have no increasing, decreasing. So now, those who did already some classification with any tools like register regression or some supervised learning, typically at the end you get something like classification table. So your classification table looks very similar to what we have here. Here you have some forecasts, like good clients, bad clients, and here you have the true values, really good clients and really bad clients. And your classification table is nothing else what you have here. And you can use, for example, the contingency coefficient of Pearson just to measure how good is your forecasting. If there is perfect relationship between your forecasts and the true values, then you have a good classification tool. If there is no relationship or your chi-squared is close to 0, then your classification performance of your classification tool is really poor. So it is directly related to any classification techniques you might have. You might also have not just 0 and 1 for classification, but for many classes, like good clients, average clients, and bad clients. So we have 3 variables here, 3 values here, and 3 values there, can be applied in exactly the same way. So that's very quickly about the descriptive statistics. In the first part, we had mean variance, histogram, box plot, and so on and so forth. In the second part, we have the measures of dependence, correlation coefficient of Pearson, correlation coefficient of Pearson, and the contingency coefficient of Pearson, which help you to capture the dependence between the two variables. Pearson measures linear dependence. One variable increases by so many units. The second variable increases or decreases by so many units. Spearman, if one increases, the second one increases as well. And by the contingency coefficient, we look at their table, like frequency table, and try to read from those frequencies if there is some relationship between the two guys or there is no relationship between the two outcomes. So I forgot to write it down here. Right here. So R x y equals to 1. So, because here we looked at their perfect values of R, like 1 and -1. It's not on the slides here, so I just write it down there. If the Spearman correlation is equal to 1, it means x increases and y increases 2. It means the pairs, all the dots lie on an increasing function. So x, I, y, I. And is equal to -1, the same but on a decreasing function. The rest is the same. So this is related to that one. And here it is the same if the correlation is equal to 0. If the correlation is equal to 0, then there is no dependence. And we have over there average is equal to spread on all 4 slots in the table. And if it is equal to 1, then we have a perfect relationship between one and the other one. Can be either like that or other way around, but there is some relationship between the gender and the grid. So that's all about this part. Now let's come to the second part. This part is kind of boring. But that's actually what we need later on in the inferential statistics. So here we talk about random variables, so I'll really jump over all the irrelevant things, like relevant but not that relevant in this way. And we'll discuss like their most important ones. Let's think about probability. So imagine you have a coin. And you want to check if it is a fair coin or not. It means you have to toss the coin and check how many heads and how many tails you have. Some guys tried that. So if you're tossed, for example, 10 times, you can get 7 times head and 3 times tail. And so on and so forth. If you do it 2,000 times, you will get 1,010 times head and 990 times tail. If you take the ratio of this one to that one, you will get something like the probability or the relative frequency of their head. This one divided by that one, it is the relative frequency of their head in their 2,000 tosses. Intuitively understand, if you proceed with a table like 20,000, 1 million, and so on and so forth, then this frequency here should converge to the true probability of getting a head or tail. But you really have to toss to infinity. So this is like an empirical counterpart of the probability, but the limiting quantity, if you literally toss to infinity, should converge to the true theoretical probability of observing a head for a particular coin. So this is like empirical probability. You just make many experiments and check how many times you should get something. And if you go to infinity and make infinitely many experiments, then your relative frequency should converge to some theoretical probability. Now, this is nice to estimate the probability, but it's very tedious. So what people typically try, they try to model this probability using some statistical tools. And to model that, we need like different types of distributions and really different statements about this probability. So let us start with some basic properties. The whole theory of probability, like mathematical statistics, was developed by Kolmogorov almost like 100 years ago. Before that time, the whole statistic was very empirical. So people usually work just with descriptive statistics. They try to characterize the data with some means, variances, some plots, and so on and so forth. And he was the first one who introduced some kind of general concept of probability, or their like mathematical treatment of probability. So he defined this function PA, the probability of the event A, in a typical mathematical style, some formulas. So the probability intuitively should be between 0 and 1. Any probability between 0% and 1%. The probability of a certain event, so omega is our probability of a certain event, is always 1. And if you unite some disjoint events, then the probability of every single element can be added together to a joint probability. So this is really a strange formula. So let's imagine that we toss a dice. So we have 6 possibilities. Either we have just 1 spot, we have 2 spots, or 6 spots on the dice. So what is the probability that we have 1 spot, 3 spots, and 6 spots on the dice? So every single of those events here is 1 AI. They are disjoint, so we cannot have 1 and 3 spots simultaneously on the dice. And according to this property of the probability, this probability should be simply the sum of the individual probabilities. So in fact, in normal language, the probability that you toss either 1 or 3 or 6, the probability that you toss 1 plus probability that you toss 3 and plus the probability that you toss 6. In total, you have just by normal dice 1 6 plus 1 6 plus 1 6 is 1/2. Very natural. We don't have a lot of math to like that, but if you try to formalize it with formulas for any number of individual events, then it looks like this third property of the probability. And now if we have a function or a mapping which satisfies all 3 properties here, we say that this function is the probability of the event A. Any type of population for any type of splitting A1 to infinity and so on. So that's what Kolmogorov decided or suggested, and then building on that, the whole theory of more formal statistic was developed. Now, those things, they are interesting, but I don't know how many of you had some kind of combinatorics at school, at the university. So we are like 20 students at 4 tables. How many possibilities are there to distribute the students over the tables? Or what is the probability of winning in a lottery if you just draw 6 numbers out of 49 or something like that? Everything goes in this direction, and those are the basic formulas how to work with. What is important is the conditional probability and conditional dependence or independence. So here we have to spend some time. In most of the cases, what we do in statistics is we deal with some conditional events. So what is your income conditionally on your education? What is your body weight conditional on your height? So everything what you try to model in statistics, econometrics, or with some data science tools is you try to say something about y knowing the value of x. So it is a conditional statement about your outcome feature depending on the values of some input features, some x's. So we talk always, or try to make some statement about some conditional events. And if you have conditional events, we're also interested in the conditional probabilities. So one basic definition of the conditional probability is that the probability of the event A given B is the probability of the joint event, that the 2 things happen simultaneously, divided on the probability of the condition B here. So let's
come back to our example with boys, girls, passed and failed. What is the probability that you passed an exam if you are a girl? This is a probability that you passed an exam and you are a girl, like unconditional probability. Divided on the probability that you are a girl. Sounds bloody, but like the fraction of girls in this. So how do we read this one? Probability of passed if, sounds also strange, but conditional it means that you have some knowledge. If you know you are a girl. So you have some knowledge, you rely on this knowledge, and you try to make some inference on about the second variable, passed or failed. Here we have an unconditional statement. So what is the probability of passing the exam and being a girl without any specific relationship between those two variables? And here is the probability of being a girl, regardless of if you passed or you failed the exam. So this is like the basic formula which defines what is a conditional event. And we'll actually later on in the econometrics work a lot with this kind of conditional probabilities and conditional implications. Probability that you passed the exam, given you are a girl, plus probability that you failed the exam, given you are a girl, is equal to 1. So if you're a girl, you have two chances, either passed or failed. So the total probability or the sum of the probabilities is equal to 1. What is important? That, for example, this one is wrong. B plus. So the same with bar, which is like alternative event or opposite event. Probability that you pass the exam if you are a girl, plus probability that you pass the exam if you are a boy, is not equal to 1. So you can swap things here in the events, but you cannot swap the things in the condition. Marina is also here. You know? It's not on mine. It should be control specific. We are not so many options. So reading. Someone?
It's
Recorded?
physically in the left right to laptop.
I just pressed something and it seems to. So you have just, you can change the variables over here and you end up with the probability of 1, but you cannot change the conditions because else you will get something. So now they're kind of messy formulas, but we'll come to an example in 2 slides and then it's going to be understandable. So below total probability of the event B given as the sum of some probabilities. So what is the probability that you pass the exam? Probability of passing the exam should be the probability that you pass the exam given you are a girl times the probability that you are a girl plus the second element of the sum, probability that you pass the exam if you are a boy times the probability that you are a boy. So a kind of nature. Probability you pass given you are a girl times the probability that you are a girl plus probability you pass given you are a boy times the probability that you are a boy. Very nature. This kind of idea is used in their ensemble modeling. So in data science, frequently you don't know which model to use. You just put many models together, and you have to combine, for example, forecasts from different models. So what you do, your forecast for something is going to be the forecast from one model, so forecast for their output feature from model, if you assume that model 1, times the probability that the given model is the correct one or the best one, plus forecast, assuming that you use a second model, times the probability that you use the given model is the best one, and so on and so forth. So you can combine really many different models to a single forecast. It's like forecast combination or model ensembles. Now, frequently you want to rotate the probability, and this is the place where the bias rule comes into the game. The bias rule is the basic idea for Bayesian learning. The Bayesian learning is also now on coming in the machine learning, because Bayesian learning helps you to introduce your own beliefs into the model, into the modeling, and to get some kind of belief-adjusted forecasts or predictions from any model. So what the idea is that we try to rotate our probabilities. So the probability for example, assume that we found an exam somewhere in the corridor, and it is not signed. You don't know if it is what is the name of the person who wrote that exam, but you know that the person passed the exam. The question is this person a girl or a boy? So what is the probability that someone is a boy if he passed the exam? So this probability is a kind of rotated thing to what we had before. So here we have passed girl, passed boy, and here it is other way around. What is the probability of being a boy if you know that this person passed the exam? And in fact, this is where our bias rule can be applied. So this is the probability that you passed the exam. That's why here boy, because else we have knowing that you are a boy times the probability that you are a boy divided on the probability that you passed. So the bias rule helps you to rotate the probabilities. Boy passed, passed boy, probability of being a boy divided on the probability of passing the exam. So sounds very artificial, but let's apply this idea to a very natural problem. It's especially in medical statistics very important. Assume that, for example, there are plenty of studies on the cancer of prostate, and you know that approximately 1% of men between 40 and 50 do have the cancer of prostate. That's 1% is pretty large. A very simple test to check if some person has this type of cancer or not is the so-called PCA test. Now, of course, this PCA test was tested zillions of times, and the people know that this test gives you the correct diagnosis with a probability of 70% if a person is healthy. It means if someone has no cancer, then this test will tell you that you have no cancer with probability of 70%. With 30%, you will, the test will say you have cancer, and then you need kind of other test or more delicate analysis of the problem. And the test gives this probability of 86.5% the correct diagnosis for ill patients. So if someone really has cancer, then this test will detect that with probability of 86.5. So those probabilities can really be computed with high precision because they are have been tested in like tens of thousands and hundreds of thousands. Now the question is, what is the probability that a patient with negative test, so the test, or let's say positive test, it means the test tells that the person has cancer, is really ill or really has cancer. So let us define the events. But maybe let's look at a diagram. So the decision tree is a kind of an easy way to decide these things. So at the beginning, we have two choices. Either the patient has no cancer or has a cancer. We know that this probability here is 1%, because just according to statistics, approximately 1% of all men between 40 and 50, they do have cancer, so this is this probability. And the probability that the person has no cancer is then 99%. So it's a priori probability. It's like probability of A, and this is probability of not A. Now, assume that we have a patient who has cancer and we run the test. The test correctly diagnoses a disease, diagnoses a disease correctly with 70% probability. This is our conditional probability over here, 70% for health. Other way around, yeah? Yeah. So 0.7, it is a probability that the test says yes. It should be given that their person has cancer, has no cancer.
Zero seven should be, in this example, 0.7 should be actually discussed, right? The correct diagnosis. The correct diagnosis here means no cancer.
That's denoted in some reasonable way. So no cancer. That's why when it's through. No. Is it blind? It's actually exactly 3. We got some timing, you see. So we have perfect timing today. So let's talk about the example then tomorrow at 9. So because it will take like 2 minutes to cover the thing. So thank you and see you then tomorrow in the morning.